Welcome to a lesson with Dr. Powell. Let's take a look at how we can determine the sizes of fibers of a function at minimum if we're given some information. Suppose that we have a function whose domain is z, the integers. We know something about this function. We know that 1 and 7 live in the same fiber of this function. We also know that this function preserves the operation of addition in the integers. And we also will know that this function is a surjection, meaning that it's basically like a merge function, and the elements of the codomain can actually be pictured in the domain as the chunks, the fibers themselves. Okay, and so there's a nice addition operation on those chunks in the codomain here, and it's transferred by this function. If it preserves, this function preserves the addition operation. Okay, let's see. Well, first, what does it mean for addition to be preserved? That means that if we add before we run the function, so we add then run the function, that's going to give us the same result as if we run the function and then we add afterwards in the codomain. So that's what it means for addition to be preserved. Let's use this fact and the fact that that 1 and 7 are in the same fiber. That's the same thing as saying f of 1 is equal to f of 7. In order to show, in order to determine what the sizes of these fibers should be. Okay, so let's kind of look at some things where we could maybe pop out an f of 1 and f of 7, and maybe find other things that are in the same fiber or as each other. 0 is actually a great thing to check out. In fact, we can get that by, let's see, if we did -1 plus 1, so 1 is one of the things we're working with, and we get f of -1 plus f of 1. Now we know that f of 1 is the same as f of 7, so we could replace this with f of 7 because that was one of our assumptions, the same fiber. And then using a further assumption that we're preserving addition, assuming that this function will preserve addition, see, we would get f of -1 plus 7, which would be f of 6. Ooh. And what is this? This was -1 plus 1 is 0. So really what we've actually just shown, we just showed that 0 and 6 must be in the exact same fiber. So 0 and 6 are in the same thing. So that means anytime you have a 0, it's replaceable by 6. And let's see how we can use that and what that actually means. So for instance, let's suppose that we had something like 1 plus 0 plus 0 plus 0. And we want to know things that are in the same fiber as 1, right? Okay, well, this is equal to 1, right? Well, you can, preserving addition, you can always do this, f of 0 plus f of 0 plus f of 0. And then let's think for a minute. See this f of 0? That's going to be the same thing as f of 6, the same thing as f of 6, the same thing as f of 6. And then what we could do is we could put all this back happening before the function, 1 plus 6 plus 6 plus 6. And actually what we've seen is f of 1 is going to be the same as f of 1 plus 6 plus 6 plus 6. Whew. So 1 plus any multiple of 6 is in the exact same fiber. As long as it's, at least right now, we're just adding positive 6s on, I suppose. But let's take a look at maybe -6 and what -6 will do. All right. Okay, so let's suppose we have something like let's do 6 plus -6. All right. We know that's 0. All right, we know that's okay. We know that that'll give us the same thing. So this is in the same fiber as 0, but we also know that this is equal to, because addition is preserved, f of 6 plus f of negative 6, which is equal to 0. And, in particular, we know that this guy right here is the same thing as f of 0, right? It's in the same location as f of 0. And with addition being preserved, okay, so that's f of 0, and that's f of 0. So we could subtract that off, and we actually get that f of negative 6 has to be 0. Okay, so f of negative 6 actually is 0 here. But we also know that f of 0 is equal to 0 and f of 6 is equal to 0 for the following reason. Well, first of all, we know f of 0 is equal to f of 6 because they're in the same fiber. But we also know that, if you did anything at all, like, let's do like f of 1. We could think of this inner one as being 1 plus 0. And then in the addition transferal, that's going to be f of 1 plus f of 0. And f of 0 by cancellation is 0 itself. So really, all these guys are 0 in the at least it's the additive identity in the codomain. So it's kind of like the 0 of the codomain. So that's kind of so this 0, when I put it here, that's actually the 0 of the codomain. It's kind of the output. So it's kind of like a chunk thing, but it's a chunk that behaves like a 0, if you will. So in that case, we actually get that that negative 6 is in the same fiber as 6 and 0. So really what we have seen then is that that 1 plus any positive or negative integer multiple of 6, which we can write as 1 plus 6z. So 1 more than all multiples of 6 is one whole, is at least, the fiber has to be big enough to contain that. Similarly for 2 plus 6z, so anything that's 2 more than they all have to be in the same chunk together for a similar reason, same with 3 and so forth. In fact, we're going to end up getting 6 different chunks. So 1 more, 2 more, 3 more, 4 more, 5 more, and then it's just simply a multiple of 6 itself. We could label these chunks as with the following notation: 0 bar is being multiples of 6, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Okay, great. So we know when we preserve addition, we know that at least these guys need to be in fibers. So then the question comes: how do we know? Do we know that this choice of fibers is the correct one? Is addition going to be completely preserved with this choice? At least we have the choice. So what we've done so far is we made a choice of our fibers. Now what we're going to do is we're going to prove that this choice is correct. Actually, addition is preserved when we make this choice for our fibers. So basically what this is, and how does the function go? What the function is basically going to do is that if an element is in this chunk, it's going to be sent to this chunk itself. If an element's in this chunk, it's going to be sent to that. So really, we've defined our function pretty much. It's a well-defined function. We just have to show now that this choice of function actually preserves addition, and we know that the fibers have to, at minimum, at least contain these in them. And so if we can prove this preserved addition, then we know that exactly this is the minimal choice for a addition preserving function where 1 and 7 had to be in the same fiber. Okay, so we'll go ahead with that. Now, in order to do this, what we're going to do is we need a way of thinking about this addition, or defining this addition kind of formally in the codomain itself. So what we're going to do is we're going to say, first of all, we're going to let A bar be equal to B bar if they are 6 away from each other. So this notation is simply going to be that no matter, like, for instance, like 13 bar is the same as 1 bar. This is just another way of representing that. So we're going to use that kind of representation, um, and um, and we're going to define the addition in the following way. So if we want to add a bar plus b bar, it's going to be equal to a plus b bar. Now, this should make sense because really what this is like f of a plus f of b, quite literally. We're just making this assumption. So this really is giving the addition. All right. So we're going to kind of be thinking about that as we go along. So for instance, let's suppose that, so if we can show that this always holds, right, for these particular chunks that we've chosen, then we're done. Then we know that that addition is preserved here. We have this. This is the definition of the addition, assuming that these bars are the chunks that we've chosen. So let's go ahead and see how we can do that. So the elements of a bar, let's take an arbitrary element of a bar. Just anything in this chunk. So let's take anything in this chunk at all, right? So that would be like a plus a multiple of 6. So 6n, say, for where n is some integer. Take anything in b bar, that would be like b plus 6m. So take anything here and anything here, and we're going to see if no matter what a is and b is, that we are we still going to get this this thing holding here. Okay, so let's take a look at that. Well, first of all, let's take this guy. So this guy is going to be replacing a in both places. This guy is going to be replacing the b in both places. And then let's look over here and let's add them together. So if we add them together, we're going to get a plus b plus 6 times n plus m. Notice that this, by our choice of fibers, this right here actually lives in a plus b. So this is actually equal to that, meaning that no matter what a is and b is in terms of our representation, we actually get that this always works. That if we take anything in, let's see, anything in a bar and anything in b bar at all, then so if we take something different than a and something different than b here, so we take any element in a bar and any element in b bar at all, just anything in this fiber and anything in that fiber, and we add them together before we take fibers, and then we look after, we actually will always get to the exact same fiber over here. So there's actually one well-defined way to get what this addition is. No matter what a is and what b is, it always will work. So this is kind of a quick little intuitive statement, but it should hold, and so we actually get that that it works in this particular case. So kind of thinking about that, what we need is that anything in so anything in this guy and anything in this guy, if we add them together before the function, it should be the same thing as adding after the function, and it is here. Basically, we're just replacing a and b by anything we want before we actually go through the function itself. That's what we did by doing these plus 6n and plus 6m here, and we still got something in there. So it still works. It still holds true as we go along for like whole chunks, move into whole chunks, and we've actually done it. Now, if we can actually formalize kind of what we're saying by thinking about it this way, if we have, so we're starting off with addition. This is like ordered pairs and integers, like first first thing in the ordered pair, second thing in the ordered pair. This is the Cartesian product of Z and Z. And so suppose that's addition, and kind of let's let P for partition, right, be like the set of the bars here. It has 6 elements in it. Okay. And so this is the addition in P here. And so kind of what we're doing is we're looking at, we add, we get down here, then we apply the function. That's like putting the bar on. Or so whenever we go here, that's like taking a bar. Or here we take bars, like to each separate thing, like to A bar and then B bar, and then we add in P. So in order for this to work, this needs to be a commutative diagram, right? So let's suppose that the only thing we don't really have yet is this guy right here, addition and P, but we have everything else kind of working just fine. How do we know that this thing actually holds? And if it does, to make this commute, then we actually have that addition is preserved. How do we know that's hold? Well, all we need is that the fiber partition of this function, which is surjective, is a refinement of the fiber partition over here of this part. And what does that mean? That means that you take anything over here, like let's suppose you have like 1 bar and 2 bar, okay, as an ordered pair, and you bring it back over here to integers. So anything that lives in 1 bar and anything lives in 2 bar, you put them together, you add them together in here, and then you take a bar, right? Okay, right. So is it, so basically what that means is, does that live in 1 fiber of this? Is that well defined? Is that not determined as 1 fiber? So let's see about that. So take anything in 1 bar. Anything in 1 bar is like 1 plus 6n. Anything in 2 bar is like 2 plus 6m. Okay. So basically anything like this. So anything, any ordered pair that looks like this would be like, that makes up the whole box that comes from here. Now, is that box contained in a box in this particular fiber? Let's see about that for now, okay? So let's suppose, okay, so we know, for instance, when n is 0 and m is 0, we get 1 and 2, and that goes to 3 bar along this way. Okay, now as we go to 3 bar, okay, so what's the full preimage of 3 bar as we go up here? So 3 bar, well, 3 bar as we go back here would be the set of all like 3 plus multiples of 6. And then through addition, what is that as we go back here? Well, that's going to be anything like, as we go back up here, well, as we go back here, and basically what we need is that we need that is 1 plus is this thing, right? So anything in here, as we add these together, do they live in here? And surely they do. So that's kind of what we showed, actually. We showed that anything that's in this preimage over here, anything in this of this guy right here, so anything in this fiber, as we send it down here, it actually, as we add these two things together, it actually lives in here. 1 plus 2 is 3, and then we have plus, we can factor the 6 from the n plus m, and surely that lives in here. Now, since that lives in here, that's actually the it lives in here, which lives in a fiber of this, so it lives in a complete fiber of this guy right here to get to this 3 bar going in that direction. So what we've actually shown is that this is, now we could have replaced this 1 and 2 with A and B, and in that case, what we've just shown is we've just shown that this, the fiber up here is a refinement of that fiber, which actually means that we actually have this going on here. So if we want to be technical, that is, we've shown that it actually works, function, that addition preservation holds for that particular choice, and that's the minimal choice that we could have had. Thanks for watching.